Hello everybody and welcome to our first lesson in Unit 4, Higher Order Polynomials. The topic of today's lesson is end behavior in graphing cubic functions, and the objective is we will determine the end behavior of a polynomial function and graph cubic functions using a transformational approach. So then let's take a step back and think about what is a polynomial really. Polynomial, the word has two parts. The first part, poly, stands for many, and nomial means term. So a polynomial has many terms. There are two things that have to be true for us to be able to call an expression a polynomial. We can have no negative exponents, and we cannot divide by a variable. And if you think about it, that really is more or less the same thing, right? Because if we have a negative exponent, then that would mean we would flip that part of the expression to the denominator, and then the variable is in the denominator, and that cannot happen. We cannot divide by a variable. A polynomial function has a general form as you see it written here. In other words, it has a whole bunch of terms and they have the same variable. They can have different coefficients and they most certainly will have different exponents, and the convention is that we write a polynomial function with the highest exponent starting, and then we go down from there, and our last term is the constant that has no variable left. Let's look at the example we have here on the left. F of x is equal to 4x to the fifth power plus 3x to the fourth plus x squared plus 2x plus 1. In order to analyze this polynomial function, we need to remember two concepts that we learned in Algebra 1. One of them is the leading coefficient. The leading coefficient is the coefficient of the term with the highest exponent. And that's why it's helpful when we have the terms ordered by exponent and we have the term with the highest exponent on the left. And then we can see that in this case, 4, the coefficient of our term, 4x to the fifth power, is the leading coefficient. The other important concept is the degree. The degree is the exponent, the highest one that you can find in that polynomial function. And we're looking at our term on the left again, and we see the exponent of 5, and that means this is the fifth degree. This polynomial function has a degree of 5. Moving over to our table on the right, we can see some different types of common polynomial functions ordered by degree. With a degree of 0, the function we get is called constant, and an example for that would be 7, just a number. There's no variable, it's a constant function. The degree is 0. If the degree is 1, we have a type of function that you dealt with a lot in Algebra 1, linear function. Just an example for that would be f of x is equal to 2x plus 6. If we have a degree of 2, we have a quadratic function. quadratic functions you are well aware of and you know them very well. The example is already in this table. F of x is equal to 2x squared plus x minus 9. A degree of 3 makes a function a cubic function. F of x is equal to x cubed minus x squared plus 3x. And if you have a degree of 4, that type of function is called quartic. And an example could be f of x is equal to x to the 4th power plus x squared plus 8. Then let's talk about the end behavior of polynomial functions. And here on this part, you see a table with a large number of polynomial functions. And in order to analyze their end behavior, the easiest and best way would be to just take the function, punch them in the calculator, and look at the graph and see what the line or curve does. Fortunately, you don't have to do that yourselves. I already did it for you. Just go ahead and copy these sketches into your notes. And again, these are just sketches. They don't have to be super accurate, but they serve the purpose. If we now look at all these graphs and we go line by line, starting with our first line, we see functions. They all have an odd degree. It's either 1 for the first two functions or 3 for the next two functions. And they have a positive leading coefficient. Let's note that here on the side. Odd degree and positive leading coefficient. I'm going to abbreviate that with capital L, capital C. If we look at our next four functions, we see that they all have an odd degree. The first two, again, degree of 1, linear functions, and the next two have a degree of 3. But this time, these functions all have a negative leading coefficient. So let's note this down too. Odd degree, negative leading coefficient. Going to the next line, now we see function and they have an even degree. We see two quadratic functions, two quartic functions. The degree is even, and for all four of them, the leading coefficient is positive. Even degree and positive lead coefficient. And last but not least, you already expected this. Looking at our last four functions, they all have an even degree, quadratic as well as quartic functions, and they have a negative leading coefficient. Let's now take a closer look at the end behavior of those functions, and let's use that box down here to summarize our findings. And again, I have already done that work for you. You only have to copy it. So let's go ahead and go through the four different cases. If we have a function with odd degree and positive leading coefficient, then the end behavior is as x goes to infinity, f of x goes to infinity, and as x goes to negative infinity, f of x goes to negative infinity. Functions with odd degree and negative leading coefficient, as x goes to positive infinity, f of x goes to negative infinity. As x goes to negative infinity, f of x goes to positive infinity. Functions with even degree and positive lead coefficient, as x goes to positive infinity, f of x goes to positive infinity. And as x goes to negative infinity, f of x still goes to positive infinity. Functions with an even degree and a negative leading coefficient, then as x goes to positive infinity, f of x goes to negative infinity, and as x goes to negative infinity, f of x still goes to negative infinity. Look at the pattern. This is important to memorize, to remember. There are different ways to look at it. For example, you can see that all functions with odd degree have end behavior going in both directions, one going up, one going down. All functions with even degree have end behavior that always goes in the same direction, either both up or both down. Functions with positive lead coefficients go the same way as the x goes, or at least they're positive. And functions with a negative leading coefficient, the end behavior goes in opposite ways as the x goes, or is generally negative. These are just different ways to think about it. Just find your own way to remember these. But we can now go back to the function that we had before, and we can now state our end behavior. We have a function with a positive lead coefficient and an odd degree and positive leading coefficient, and that means as x goes to infinity, f of x goes to infinity, and as x goes to negative infinity, f of x also goes to negative infinity. And we did all that without even having to graph this very complicated function or using the calculator. Well done, you guys. Now go ahead and watch the second part of this tutorial.